Hi, it's Ms. Moser, and I wanted to talk with you about ionic versus molecular compounds. How they're bonded, you kind of know that, but how those bonds make their properties different and make the compounds actually behave differently. So, in a molecular compound, of course, the atoms are actually, well, we could say holding hands. They're sharing electrons, they're physically overlapping their fuzzy bits. It's as though, if you remember the metaphor of the little tiny tennis ball surrounded by feet and feet and feet of cotton candy, the electron cloud with the electrons zipping all around. They've actually not only overlapped their cotton candy clouds, they've kind of woven them together, tied them together, if you will, so that those electrons have places to orbit. In an ionic compound, of course, it's a different situation because they're not physically joined. They're very strongly attracted, sort of standing shoulder to shoulder, but not holding hands. In a molecular compound, these bonds in between the atoms within the compound are incredibly strong. They are physically connected. They're joined physically, overlapped, tied together, however you want to think about it. But between this molecule of sugar and the next molecule, of propane, these are molecules of propane, the forces between them, well, they slip past one another. No big deal. They slide right past one another. That sliding past one another is what you see when you heat something, and it goes from being a solid, where the pieces are in fixed positions, to being a, what's that thing again? Oh yeah, a liquid. So molecular compounds, because of the fact that the bonds of attraction between the individual molecules are not terribly strong, tend to have, lower melting points. Interesting. Where in an ionic compound, despite the fact that they're not connected physically, they're just standing shoulder to shoulder, if we look at it, if we look at the overall picture, and we look at each one of those atoms with a positive or negative charge, within a big chunk of, let's use salt, sodium chloride, like the big salt crystal that lives on my desk, within that chunk of sodium chloride, every single one of these positive sodium ions is attracted to every other chloride ion out there. So you've got strong forces of attraction running from multiple positive ions to multiple negative ions. And conversely, every single negative ion is attracted to every single positive ion. So despite the fact that they're not holding hands, so to say, they're not physically connected, they're just standing shoulder to shoulder, the mass of weight of all those attractions makes for really strong bonds between all the parts of salt or any other ionic compound, which means that it's harder to get them to slide past one another when you heat them up. What would that be? Oh yeah, melting. So ionic compounds tend to have higher melting and boiling points than molecular compounds. You might think about that in terms of what you saw melt in the lab. Now, the other interesting thing about ionic compounds is they tend to be hard, but they also tend to be very brittle. So, if we imagine this chunk of salt, we might be able to see why. So we've got this chunk of sodium chloride, and it's very neatly lined up in a very well-ordered grid pattern, so that every positive charge is as close to as possible to every negative charge without getting too close to another positive charge. But if we come along with, let's say, a big old hammer and whack this thing, whack, what's going to happen? Well, what's going to happen is we're going to create a split. And, while I get rid of my border here for a second, all of these guys are going to shift downward. Well, at the point when they shift downward, what now happens? Instead of those powerful forces of attraction between positive components and negative components, what we now have is an actual force of repulsion between two positives, between two negatives. That makes this substance very brittle. The minute you tap it and those atoms become differently aligned, it sort of shatters, it falls apart, because now instead of attractive forces holding it all together, it's actually got repulsive forces, sort of blowing it up. So, let's think about ionic compounds and solubility in water, as well as their behavior once they are dissolved. So if I take my nice little chunk of salt here, and again, I'll remove that outer edge, and I drop the whole thing into a nice beaker of water. Maybe I swirl a little bit or something else to get it to dissolve. What begins to happen is that water molecules start to work their way in between these ions, because remember, water is one of those molecules that has a region of partial charge on its ends. If we think about Mickey Mouse, Mickey's little ears are happy. The hydrogens have regions of partial positive charge, and Mickey's little chin is sad. The bottom of the oxygen molecule, or the bottom of the oxygen atom, has a small region of negative charge. The fact that water is charged allows it to get into this sort of matrix of positive and negative charges and get between them and divide them up and break them up. So ionic compounds tend, because of this, to be quite soluble in water. The other thing, of course, is that once all of these little ions are moving around freely in the water, they have electrons to trade. And what it means is that you have electrons in this solution that are now capable of going someplace. What's the flow of electricity? Well, it's the flow of charge. And once we've got all these dissolved ions in the water, we've got a situation where charge can really flow. This means that ionic solutions tend to be conductive, either when they're molten or when they're dissolved in water. You'll want to look at the results of the conductivity test to see what that means for your groups. That leaves us with one last group that we're going to talk about in terms of how their underlying atomic structure influences their properties, and that's the metals. So if we think about the metals, and here we're thinking mostly about the transition metals, but this applies also to the alkali earth and alkali metals, groups 1 and 2. Those metals, though this is most obvious in the transition metals, tend to have a couple of electrons in the outer energy levels and tons of empty space. If we go back to the dorm room analogy for electrons filling up orbitals, it's as though you just moved onto a floor in a dorm where you and your roommate are the only people living there, and there are 15 rooms. You might as well sleep in a different room every night. What the heck? So these vacant orbitals tend to overlap themselves in the metals, and the electrons do just what you and your roommate are suggesting. They wander from orbital to orbital. These are called delocalized electrons because they don't have a single home. They kind of wander. What they end up doing is forming this sort of soup of electrons around all the little positive nuclei. What would that look like? What this arrangement gives us is powerful forces of attraction between each nucleus and all those electrons. Whether they started out, I'll put it in air quotes, belonging to that nucleus or not. Now they're sort of all one big family. This means that you have forces of attraction running in multiple directions throughout the metal. And here we are talking only about metals bonding with other metals. It's also sometimes referred to as the sea of electron bonding model. We call it metallic bonding. What does it do in terms of the characteristics of metals? Well, one thing it does is it allows them to be fantastic conductors of electricity. Why is that? Well, you got a bunch of electrons that are free to roam the halls. And what are those electrons carrying? Charge. What is electricity? The transfer of charge. And you've got tons of little charge carriers, the electrons, free to roam in any direction. It also allows metals to be malleable, to be rolled into thin sheets, and ductile, to be pulled into wires. So if you remembered, with ionic compounds, when we hit it with a hammer, suddenly none of the charges lined up, and the forces inside were actually now repelling one another. So we no longer have something that's holding together, we have something that's shattering. In a metal, if we hit it with that same hammer, it's just going to kind of compress the sea of electrons. There's no formal rigid alignment to be maintained, so the forces of attraction still continue to operate in all directions throughout the material. That's what makes metals metals. Okay, we'll pick it up next week with polyatomic ions. You have some additional homework problems assigned. They're listed on Classroom. Have a great weekend.